Come on, my dears, we begin with chapter number 7. Is a bit long, very interesting, very important also. Okay, the title of the chapter is Semiconductor Electronics, Materials, Devices and Simple Circuits. Okay, fine. Let us see about discovery of electron and its introduction. In the previous chapter, we had studied that electron was discovered through the experiments on conduction of electricity in gases, and it was also proved that electron is one of the fundamental particles taking part in the composition of any material. Okay, fine. Now we go for what is called semiconductor. Depending upon the level of electrical conductivity, different elements are categorized into 3 categories. First is that having very large electrical conductivity, we call them good conductors of electricity. Correct? Fine. Second is that which has very low value of electrical conductivity. They are called poor conductors or insulators of electricity. Correct? And there are elements whose electrical conductivity is smaller than that of good conductors but greater than that of insulators. Such elements are called semiconductors because their electrical conductivity is in between good conductors and bad conductors. Correct? We call them semiconductors. Okay, fine. The known semiconductors are silicon and germanium. We will call them elemental semiconductors. Elemental or fundamental semiconductors. They are silicon and germanium. Okay, fine. Now let us see what is called an electronics. What is called an electronics? Electronics is a word which is coined by these 2 words. By coining these 2 words, we have prepared this word which is called electronics. Which 2 words? Electron plus mechanics. Electron plus mechanics. If you coin these 2 words, then the word prepared is electronics. Okay, what do you mean by an electronics? I am showing you. Just consider a metallic wire. Okay, across the 2 ends of that metallic wire, you just go on applying different values of electric potential difference, and at the same time you try to measure the amount of electric current passing through that wire. Practically we can measure it. And then after we can plot a graph of current passing through a given metallic wire versus potential difference applied across the 2 ends of that wire. Fine. When we plot that graph is found to be a straight line. Graph is found to be a straight line. And whenever you get straight line graph, it indicates linear relationship. And when I is proportional to V, come on, it is nothing but application of Ohm's law. Correct? Whenever Ohm's law is obeyed, you will get graph of I versus V as a straight line graph, and that indicates I is proportional to V. Correct? In short, in metals, current will be always set up in such a manner such that Ohm's law can be obeyed. Fine. But in practice, we require current of different nature. We require some different I versus V characteristics. For example, we require such a characteristic in which if the voltage changes between these 2 limits, then we can see in the graph that current value remains constant. Now tell me, if you want current to remain constant between these 2 voltage values, now the question is, can you get such a current through metallic wires? Never, because in metallic wire, whenever voltage will increase, current will increase proportionately. It will never become constant like this. Correct? So what does it mean? That the graph or I versus V characteristic which you require in practice cannot be obtained using metallic wires, correct? Then you know what the scientists have done? Because the electrons, if they remain inside the metal, they will flow and they will constitute that current which can obey Ohm's law. Then we will not have such characteristic, correct? Because we want I versus V characteristic according to our desire, according to our requirement, you know what we do? We eject electrons out of the metal. We eject electrons out of the material, and then after, on the number of electrons emitted, on their flow, on everything, we put our own control. And then after, we prepare such devices, we study them and we put them in applications in our day-to-day life. This everything is done in one branch of physics which is called an electronics, correct? Preparation, study and use of those devices. Preparation, study and use of those devices in which we have our own control on the number of electrons emitted, on their flow, and in which we obtain desired I versus V characteristics is called an electronics. I repeat, the construction, study and use of those devices in which we have our own control on the number of electrons emitted, on their flow, and in which we obtain desired I versus V characteristics is called electronics. Got it? Fine. Now, earlier it was the vacuum tube electronics, which was also known as valve electronics, that was in commencement, that was in use earlier, but nowadays it has been replaced by better electronics which is called solid state electronics. How solid state electronics is superior to valve electronics? Because of some reasons. See those points of reason. First of all the devices which are made from solid state electronics, they are found to be quite small in volume. So they can be made easily portable. You can shift them very easily from one to another place. Secondly, they are very much light in weight. Very much light in weight. Thirdly, third point is they are quite cheap in cost. They are quite cheap in cost. So they are quite affordable. And last point, for various applications in market, they are available in a very wide range. Depending upon our requirement, we can choose the proper electrical appliances from this solid state electronics. Correct? Fine. Then after, in this chapter, further we are going to study in solid state electronics about PN junction diode, Zener diode, light emitting diode, shortly written as LED, light emitting diode, then photodiode, solar cell, then after we will talk about digital electronics and some logic circuits in that. Okay, fine. There are certain compounds, they behave like semiconductors. Which are those compounds? You will require to remember their examples because they are given in the textbook. Those examples are, look here, CDS, that is cadmium sulfide, and this is gallium arsenide, this one is cadmium selenide, okay, fine. These are the compounds which behave like semiconductors, fine. Now, we have such semiconductors, we have such compounds, might be carbonic, might be non-carbonic, and might be polymer, correct? About all this you will study in your higher standards, and that sort of electronics is called polymer electronics, or we call it sometimes molecular electronics. About polymer electronics or molecular electronics you will study in your higher standards, okay? Fine. Now let us see crystalline structure of silicon. Atomic number of silicon is 14. So I am writing here Z equals to 14. What do you mean by Z equals to 14? Number of protons inside the nucleus of one atom of silicon is 14, and outside the nucleus we have equal number of electrons. So there are 14 electrons in each silicon atom. Now these 14 electrons, if you arrange depending upon their different values of energy, then you will have electronic configuration like this: 1s2, 2s2, 2p6, 3s2, 3p2. 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 2, that is 14, correct? So this is how the silicon atom has this electronic configuration, okay? Now, with this 2 electrons from 1s, K shell is completely filled up. With this 6 plus 2, 8 electrons by 2s orbital and 2p orbital, this L shell is completely filled up. But with this 2 plus 2, that is 4 electrons, this M shell is not completely filled up. It is partially filled up. It is partially filled up. And electrons in the outermost orbit of an atom, which is partially filled, are called valence electrons. Electrons in the outermost partially filled orbit of an atom is called valence electron. Because there are 4 valence electrons in each silicon atom, we call silicon atom as tetravalent. We call silicon atom as tetravalent. Why tetravalent? Because it has 4 valence electrons, correct? Had it been 5 valence electrons, we will call it pentavalent. 3 valence electrons, trivalent. But 4 valence electrons, then tetravalent. Got it? Fine. Likewise, remember, germanium is also tetravalent. Germanium is also tetravalent. Silicon and germanium, both of them are tetravalent. Atomic number of silicon is 14. Atomic number of germanium is 32. Okay, fine. Now tell me, here it so happens that 2 orbitals of 3s and 2 orbitals of 3p, 2 plus 2, totally 4 orbitals are getting mixed up, and because of the process of hybridization between these 4 orbitals, ultimately we have 4 sp3 orbitals, 4 sp3 hybrid orbitals, 4 sp3 hybrid orbitals. And as one silicon atom has this many hybrid orbitals, similarly its surrounding silicon atoms also have same number of sp3 hybrid orbitals. And then after, there is some covalent bonding between neighboring silicon atoms. How is that bonding? How is the unit cell of this crystalline structure of silicon? I am showing you. See, in the figure you will find a bound figure which is bound by 4 identical triangles. Because it has 4 faces, we call it tetrahedron. What is it called? Tetrahedron. The shape is called tetrahedral shape. It has 4 identical sides in the form of 4 identical triangles. Which 4 triangles I am showing you? This is one triangle, then this one is second triangle, this one is third triangle on the back side, and this one is fourth triangle in the base. Okay, so there are 4 triangles. Fine. Now, in the center of this tetrahedron, if you imagine one silicon atom, then for this central silicon atom, where are its closest neighboring silicon atoms? They are found to be located at the vertices of the same tetrahedron. That's why here also I am showing you silicon atom. This blue colored big empty circle indicates silicon atom. Okay, fine. Now tell me, how many valence electrons does this silicon atom have? It has 4 valence electrons. Similarly, these all 4 located at the vertices, they also each of them have 4 valence electrons. Now what does this do? It gives 1 valence electron and it gains 1 electron. It gives 1 electron, it takes 1 electron. That is how, by sharing of 2 valence electrons, it forms 4 covalent bonds. And those 4 covalent bonds I am showing here in the figure like this. Okay. So these are the 4 covalent bonds, and in each covalent bond there are 2 electrons. One is given by this silicon atom and one is accepted by it. Okay. one is given, one is taken, one is given, one is taken, like that. By sharing of 2 valence electrons in each bond, we have in all totally 4 covalent bonds surrounding to silicon atom. Now this is a unit cell. If you want to expand this structure in 3 dimensions, you know what you should do? You should take these silicon atoms which are located at the vertices at centers of other 4 tetrahedrons, and then at the vertices of those 4 tetrahedrons, how many vertices? 4 4s are 16 vertices. You can place 16 silicon atoms, and then after taking those silicon atoms at the centers of 16 tetrahedrons, you may then put other 16 4s are 64 silicon atoms at the vertices of those 16 tetrahedrons. That is how you can go on extending this structure in 3 dimensions. The real structure is 3-dimensional, but just for the sake of convenience, in figure we will show 2-dimensional crystalline lattice of silicon. That 2-dimensional crystalline lattice is shown here. Correct? Fine. Now here you can see all atoms are identical. They are all showing you atoms of silicon. Correct? When all atoms are made up of same element, then we call this crystal, we call this lattice as pure crystal. Pure crystal. Okay, fine. Or this is a pure semiconductor because there is no impurity. So it is called pure semiconductor. Fine. Such a pure semiconductors are also called intrinsic semiconductor. Intrinsic semiconductor is that pure semiconductor which is not having any impurity, okay, in which all the atoms are made up of same single element, okay, and that single element is right now silicon. Fine. Now here, while showing this lattice in 2 dimensions, we must take that care that each silicon atom should be surrounded by 4 covalent bonds, and in each covalent bond there should be presence of 2 valence electrons. Yes, accordingly I have shown here also. You can check each silicon atom is surrounded by 4 covalent bonds, and in each bond there are 2 valence electrons. Okay, fine. Now let us talk about conduction of electricity in this pure semiconductor at absolute 0 temperature. Absolute 0 is 0 Kelvin or minus 273 degrees centigrade. Correct? At this lowest temperature, you know what happens? Actually, nothing happens. Actually, nothing happens. All these atoms are found to be fixed at their respective equilibrium positions. Not only that, all these valence electrons also remain very much engaged in their respective covalent bonds. Out of the whole crystal, not a single electron is let free. If there is not a single free electron, then in the absence of free or mobile charge carriers, naturally such pure semiconductor will not conduct electricity. So such pure conductors, such pure semiconductors, in the absence of free or mobile charge carriers, they will not conduct electricity, and when they do not conduct electricity, you can say they are insulators of electricity. They are insulators of electricity. So any pure semiconductor will behave like insulator of electricity at absolute 0 temperature, that is at 0 Kelvin or minus 273 degrees centigrade. Got it? Fine. Now let us raise the temperature. Okay? But before we raise the temperature, I would like to explain you same reason using another approach, and that is using energy band diagram. Using energy band diagram. Fine. See, if you calculate energy of electron in the valence band, I mean in the if you calculate the energy of valence electron, then in this semiconductor we find that values of energy of all valence electrons are found to be very close to each other. And because the values of energy are very close to each other, their respective energy levels are also very close to each other. So they are very much close, as if they form one band. But because this band consists of energy levels pertaining to energy values of valence electrons, we call this band as valence band. Okay. So here I have shown valence band. Fine. And now, according to Pauli's exclusion principle, we find that in each energy level in this valence band, there can be only one valence electron. That's why in each energy level I have shown one valence electron. Okay, fine. Now, above this valence band, there is a region in which no energy levels are defined. No electron has energy value which is above this and below this, correct? So in this range, in this region, we do not have any energy levels, and that region in which there are no energy levels, it is called forbidden gap or forbidden region. Forbidden gap or forbidden region. Fine. Now above that forbidden region, again we have defined energy levels. And here also the energy levels are very close to each other, as if they form one band. And because electron coming in this band is responsible for conduction of electricity, we call that band as conduction band. What do we call it? Conduction band. So at the bottom we have valence band, at the top we have conduction band. And between these two we have the region in which there are no energy levels, so we call it forbidden region. Fine. This energy gap, it is shown by symbol Eg, and that energy gap, how you can define it very precisely, I am showing you. The difference in energy between lowest energy level of conduction band and topmost energy level of valence band is called energy gap. I repeat, difference in energy between lowest energy level in conduction band and highest energy level in valence band is called energy gap, shown by symbol Eg, correct? For metals there is no energy gap. For metals there is no energy gap. For semiconductors, this gap is less than 3 electron volt, and for insulators it is normally more than 5 electron volts. Okay, for semiconductors this energy gap is less than 3 electron volt. Okay, fine. Now when you are talking about absolute zero temperature, at that temperature all the valence electrons have occupied this valence band completely. One electron is there in each valence energy level. Fine. So this band is completely occupied, and because these electrons do not have any energy to migrate, to transit from this band to this band, here there is not a single valence electron. There is not a single electron here, correct? So because of absence of this electron in this band is completely empty, So conduction band is found to be completely empty at absolute zero temperature in case of pure semiconductor. Okay, fine. Now tell me, because there are no electrons here in the conduction band, naturally conduction of electricity will not be possible, and because there is no conduction of electricity, you can say pure semiconductor will behave like insulator at absolute zero temperature. Okay. So the same phenomenon we have explained on the basis of this energy band diagram. Fine. Now let us raise the temperature. Let us raise the temperature. And suppose we keep the temperature, say room temperature. Okay. You know, at room temperature what happens? All these atoms, they start vibrating. They start oscillating about their respective equilibrium positions. Fine. Now when these atoms start vibrating, we call their vibrations as thermal vibrations, because energy required for vibration is absorbed from the surrounding in the form of thermal energy. That's why we call them thermally induced vibrations or thermal vibrations. But now when all the atoms have started performing thermal vibrations, it so happens that at some typical positions, at typical moments of time, it so happens for certain atoms that their amplitude of oscillation increases beyond a certain limit. And for a given atom, if amplitude of oscillation increases beyond a certain limit, then it so happens that out of the 4 surrounding covalent bonds, one of the bonds is getting broken. Listen, say for this bond, because of thermal vibration, suppose this bond is getting broken at point C, this bond is getting broken. If this bond is getting broken, look here, then electron has escaped out. And because electrons has left this space, electron has escaped from this place, then this position is lying now empty. Okay, this position is now vacant, and that electron which has escaped from this bond, that has gone anywhere else, correct? Suppose it has come over here. When it starts performing random motion, it may come here also, correct? So the electron which has left this position has come over here. Fine. Now tell me, because of thermal vibration, suppose the covalent bond at point B is also suppose getting broken. If this is getting broken, then here also the space will be vacant. Fine. Now tell me, the electron liberated so is suppose this electron. Now tell me, this electron as such can perform random motion. But now what we do, we apply some potential difference across this crystal. Suppose this end is positive and say this end is negative. So on this negatively charged electron, this positive end will provide electrostatic force of attraction. Come on. When this is electron, you know electron is a negatively charged particle which will be always getting accelerated in a direction opposite to electric field. Electric field is from positive to negative this way, correct? And in just opposite direction, this electron will be accelerated. So now along with the random motion, this electron is accelerated towards the right hand side, that is towards positive end. And then it may so happen, it may come very close to this vacant space. If it comes in the vicinity of this vacant space, it may combine with that vacant space. And again this covalent bond is reformed, restructured. Okay, why? Electron has gone from this vacant position to this vacant position. Why it associates with this vacant position? I am showing you the reason. Earlier when electron was here, this atom was stable because it was electrically neutral. But the moment this electron had left this space and it had come over here, since that moment this atom no more remained electrically neutral. It got converted into positive ion, and then electron which has left from this space has come over here. Since that moment this atom started behaving like positive ion. So it had a tendency to grasp one electron, to grab one electron and just to provide it accommodation in this vacant position. Fine. So in the same circumstances, if any other electron is just moving around this space very close to it, then naturally it will be trapped in this vacant position. Fine. Now tell me, as if this electron is getting attracted in this vacant position. Tell me, electron has a negative charge. Who can attract negative charge? Positive charge. So you can say this vacant space behaves as if it is a positive charge. Actually there is no charge inside, but behaves as if it is a positive charge, and it has a tendency to attract electron. Such vacant space which behaves like a positive charge and which has a tendency to attract electron is only known as hole. So we call it hole, correct? Fine. No doubt you can call this as hole as long as it is unoccupied. But once any other electron has occupied this hole, then after it is no more a hole. But now, because electron had migrated from B to C, now you will find hole at position B. The same electron has gone from here to here, correct? Fine. Now tell me, this electron has gone from here to here, so now hole appears at point B. Fine. Now tell me, what can be the definition of hole? Vacant space created by breaking of covalent bond in the crystalline structure of any semiconductor at room temperature, which behaves like a positive charge and which has a tendency to attract electron, is only known as hole. Any vacant space created by breaking of covalent bond in the crystalline structure of any semiconductor at room temperature, which has a tendency to attract electron, which behaves like a positive charge, is known as hole. Correct? Fine. Now remember, hole is our ideal imagination only. It is no more a realistic particle. Hole is not a particle. Fine. Now tell me, suppose because of thermal vibration, the bond at A also gets broken. If this bond is getting broken, look here, then here also hole will be created and the electron liberated is suppose this. Now this electron will get accelerated in a direction opposite to electric field. So this way, and if it is moving say randomly, at the same time it is getting accelerated also, and it is likely to come very close to this hole, then it will combine with this hole. Once this electron combines with this hole, now this is no more a hole. This is no more a hole. Now you will find hole at point A. Tell me, earlier where was the hole created? Hole was created first at point C. Later on it got created at point B. Later on it got created at point A. So as if hole seems to be in motion from C to B to A. From C to B to A, that is here towards left side, But then the electron which was here, it was very much bound with this in this bond, and then after it became free. Once again it got engaged here. Once again it became free. Once again it got engaged over here. So see, this is that electron which is passing through several bound states. Any electron which is jumping from one hole to another, another to still another, like that, from first to second, second to third, like that, and it is passing through several bound states, such electron is called bound electron. What is it called? Bound electron. And bound electron is a realistic particle, and when it moves from A to B to C toward right hand side this way, that is toward this positive end, at that time the hole seems to be in motion in just opposite direction from C to B to A. Don't say hole moves, never. Hole seems to be in motion. Hole seems to be in motion because hole is not a realistic particle. Correct? Fine. Now, at room temperature, at some other positions also, covalent bonds are broken. Suppose covalent bond is broken here. This covalent bond is broken and hole is created here. And this is the liberated electron. Say this covalent bond is also broken. Then hole is created here and this is the liberated electron. Now tell me, these freed electrons also will get accelerated towards this positive end. So these all electrons will start moving towards positive end this way. Fine. And when these electrons are in motion towards positive end, at that time, if they happen to come very close to some hole, then they may associate. But during their journey, if there is no hole coming in the way, or they do not happen to go very close to any hole, they may not combine with the hole. And then when they are moving, and if they are not combining with any hole, when they are not combining with any hole, they remain single, they remain all alone. And such electrons which are not coming in the bound state, then we call them free electrons, because during their entire journey they remain free, independent. So we call them free electrons. So we have here motion of two types of electrons. Come on, motion of bound electrons also and motion of free electrons also. Both of them are moving towards positive end. But then what is the difference between their motion? Whenever free electron is moving, it does not create hole in just opposite direction. No. But whenever bound electron is moving, it definitely creates hole in just opposite direction. This is the difference between their motion. Now onwards, if anybody says that conduction of electricity is due to hole, you should understand that conduction of electricity due to motion of bound electron. The difference is if bound electron is moving towards right, then hole seems to be moving towards left. Okay. Here, no doubt, we get motion of two types of electrons. One is bound electrons, another is free electron. But then also, when we connect here, say microammeter, it hardly shows few microamperes. It means to say, here electrical current is very low, of the order of microampere, 10 raised to minus 6 ampere. It is very low. I mean to say, electrical conductivity of this semiconductor is at present very low. Now that low conductivity we have to explain again using energy band diagram. How to explain? I am showing you. Here I am showing, come on as usual, which is the lowest band? It is valence band. I have written here valence band. Which is the highest band? It is conduction band. Fine. Now tell me, each valence electron has occupied one valence energy level in the valence band, which are shown by yellow dots. Fine. But out of that large number of valence electrons, it so happens at room temperature, some electrons get energy in the form of thermal energy, which is greater than this forbidden gap. If energy absorbed is greater than forbidden gap, naturally such electrons will make a transition from valence band to conduction band. That is why if this electron is migrating from here to here, it will simply make this energy level vacant, and so you will have vacant position here, correct? And in the absence of electron, that vacant space created is nothing but a hole. So as many electrons will transit from valence band to conduction band, here we will have that many holes. And that electron migrated from here to here, I am showing here by yellow dots. So these are the electrons coming in the conduction band. Now tell me, here number of electrons coming is very small number, and compared to that small number, the number of vacant energy levels in conduction band is very large. Number of electrons is very few, number of vacant energy levels is very large. Then what do these electrons do? They simply perform their motion from one energy level to another, second to third, third to fourth, and so on. So they just move about in conduction band very randomly, very freely, without any opposition. That's why we call them free electrons, because their movement is executed very freely. We call them free electrons, correct? And when they are just moving from one to second energy level, second to third, like that, they conduct electricity because they are free, they are mobile charge carriers. So because these electrons are responsible for conduction of electricity, we call this band as conduction band. We call it conduction band. But because that number is very small, no doubt conduction is there, but it is a very low value of electrical conductivity. And then you can say in this pure semiconductor, we get conduction of electricity by a very small amount. Its electrical conductivity is very low, correct? Have you marked one thing? As many holes here, that many free electrons here. I mean to say, free electron number density in conduction band and hole number density in valence band, they are equal. They are equal. So I am writing Na equals to NH. Na equals to NH. Free electron number density in conduction band and hole number density in valence band, they are equal. But this thing is true for pure semiconductor without any impurity. Got it? So my dears, just now we have seen that pure semiconductors have very low electrical conductivity at room temperature also, correct? Then how to raise that level of electrical conductivity? There are three ways you can raise the level of electrical conductivity of pure semiconductor. First, you can make incidence of some proper radiation with proper frequency or wavelength, where it causes large number of charge carriers to get freed, and that's why we have level of electrical conductivity raised. Okay, we have more conduction, fast conduction of electricity later on, correct? Second way, to increase the temperature of this crystal, When you increase the temperature, naturally more covalent bonds are broken, releasing more number of free charge carriers and increasing the conduction of electricity. And third and final way, which we will study in detail, it is the way of doping. When you want to increase the conductivity of a pure semiconductor at room temperature, the third way is to add some proper impurity with proper amount at the time of growing the crystal. Such process is called doping the crystal. Doping any crystal means adding suitable impurity with suitable amount at the time of growing the crystal is known as doping. When you dope any intrinsic semiconductor, it no more remains pure semiconductor. Now it is to be called as extrinsic semiconductor. Extrinsic semiconductor. Okay. Now, by way of doping, we can prepare two types of extrinsic semiconductors. One is called N-type semiconductor. Another is called P-type semiconductor. Now, what do you mean by N-type semiconductor? What do you mean by P-type semiconductor? Why the name is like that? Let us see one by one. First of all, focus here on this N-type semiconductor. If you want to prepare N-type semiconductor out of tetravalent pure semiconductor, you are supposed to add pentavalent impurities in that. And just remember three examples for pentavalent impurities. Come on, arsenic, phosphorus, antimony. Arsenic, phosphorus, antimony. Out of which we concentrate on arsenic. Arsenic has got atomic number 33. With a 32 atomic number, germanium is tetravalent. So with 33 atomic number, this arsenic would be pentavalent, because it has 5 valence electrons. 5 valence electrons are there, so we call it pentavalent. Fine. Now, what is the proportion of impurity? I am showing you. For approximately 10⁶ silicon atoms, that is 10⁶ purity atoms, the proportion of arsenic or impurity atom is just 1. Correct? Then in 1 mole, you know 1 mole means what? Avogadro number, that is 6.02 into 10⁻23. You just discard 6.02, consider only 10⁻23. In 1 mole of crystal, you will have 10⁻23 silicon atoms approximately. For every 10⁶ silicon atoms, number of arsenic atom is 1. Then for 1 mole silicon atoms, that is approximately 10⁻23 silicon atoms, how many number of arsenic atoms? Let us find out. This into this upon this. So it will give you 10⁻17 arsenic atoms. How many? 10⁻17, which is a very large number in 1 mole. Correct? Now tell me, when you dope any crystal, what will happen? At certain positions, the place of host will be taken by guest. Place of host is taken by guest, meaning thereby place of silicon will be taken by arsenic. Suppose this is arsenic atom. Suppose if this is arsenic atom, then because it is pentavalent, it will have 5 valence electrons. 5. Out of 5 valence electrons, it will just donate 1 it will just share 1 valence electron here. In forming 4 covalent bonds, it will give 4 valence electrons. Out of 5, 4 are utilized in forming these 4 covalent bonds. Still, the 5th electron is extra. That 5th electron I am showing here. Mind well, this is loosely bound with the nucleus, correct? Now, by calculation, we have come to know that if this such excess electron, such extra electron is provided, simply 0.05 electron volt of energy from outside, then it will be getting detached from the binding with the nucleus of this arsenic atom. And what does this crystal do at room temperature? It absorbs thermal energy from the surrounding. That absorbed thermal energy is certainly greater than 0.05 electron volt. So certainly this electron has become free. Fine. So because this electron has become free, you can say with the inclusion of 1 arsenic atom in this tetravalent crystal, it gives 1 electron. It gives 1 free electron. So because it gives, we can say it donates 1 free electron to the host crystal. This guest atom donates 1 free electron to the host crystal. and because such pentavalent impurities donate free electrons to the host crystal, we call them as donor impurities. We call them as donor impurities. So remember, pentavalent impurities are also called donor impurities. Okay, fine. Now tell me, with the inclusion of one arsenic atom, if you have one free electron, then for inclusion of this many arsenic atoms in 1 mole, we will have same number of free electrons in 1 mole. So if this is 1 mole crystal, then we will have 10⁻17 number of free electrons. So number of free electrons would be very large. Number of free electrons is very large. Fine. But at room temperature, few of the covalent bonds are getting broken, and whenever any covalent bond is getting broken, it releases one pair of free electron and hole. It produces, one pair of free electron and hole. If this bond is broken, then it will produce, one pair of free electron and hole. But at room temperature, number of covalent bonds are broken with a very less number. And at room temperature, if very few covalent bonds are broken, then we will have very few holes, correct? The electrons which are released, which are made free, will add in this number. But number of holes created so by breaking of covalent bonds at room temperature is very small. That's why I am showing you here very few holes. Now here there are two types of charge carriers. Number 1, free electrons which have negative charges, and number 2, holes which behave as if they are positive charges. But because free electrons are very large in number, we call them majority charge carriers. Free electrons is called majority charge carrier. Majority charge carrier is in the form of free electron. Electron has a negative charge. The word is negative. The first letter of the word negative is N. That's why we call this semiconductor as N-type semiconductor. N-type semiconductor is that semiconductor in which the majority charge carriers are negatively charged free electrons. Got it? Fine. Here you may find number of free electrons very large, but please don't be misguided that this is electrically negative. No, it is not electrically negative, it is electrically neutral, because if this is silicon atom, then inside the nucleus we have 14 protons, and outside in all we have 14 electrons. Particular electron might not be here, but might be anywhere, but it is definitely within the crystal. If you are talking about arsenic atom, then there are 33 protons inside the nucleus and there are 33 electrons outside the nucleus, correct? So I mean to say, whether it is arsenic atom or silicon atom, because all the atoms are electrically neutral, the whole crystal is also electrically neutral, correct? Fine. Now, how to explain the conduction of electricity in this N-type semiconductor using band diagram? I am showing you. Come on. Lowest band is valence band. The energy of electron in valence band I am showing by symbol EV. Highest energy band is conduction band. The energy of electron in the conduction band I am showing by symbol EC. Now, by calculations we have come to know that value of energy of donated free electron is found to be very close to this conduction band, and they are very large in number. So I am just showing very small horizontal line segments at the same height because they have same energy, and because that energy is very close to conduction band, I am just showing them very close to this conduction band, correct? Now tell me, there are one electron in each of these horizontal small line segment, and then after tell me, this gap is found to be very small as 0.05 electron volt. Now at room temperature, this crystal is continuously absorbing thermal energy from the surrounding, and that absorbed thermal energy is definitely greater than this. When it is greater than this, naturally all these electrons will simply make transitions from their existing energy level to the higher energy levels in the conduction band. Now tell me, so we have here very large number of electrons in the conduction band, but compared to this number of electrons, we have vacant energy levels in this conduction band very large in number. So any electrons just can move about randomly anywhere from one energy level to second, second to third, third to fourth and so on, correct? Because each electron is quite free to execute its random motion in any energy level which is vacant in the conduction band, then we call these electrons as free electrons. We call them as free electrons. And because they move randomly through their random motion, electricity is conducted. Because these electrons are responsible for conduction of electricity, we call this band as conduction band, correct? And because they are very large in number, majority charge carriers are in the form of negatively charged free electrons. But mind well, at room temperature it so happens that some of the electrons lying in the valence band, they get energy more than this forbidden gap. If they get energy more than this forbidden gap, naturally they will make transition from valence band to conduction band, and they will add in the number of free electrons, and from whichever position, from whichever energy level they have been migrated, at that position we will have creation of hole. But at room temperature, very few electrons migrate this way from valence to conduction band. That's why we have very few holes here, very few holes. Very large number of free electrons, very few holes, okay? So naturally electrons are becoming now, free electrons are becoming now majority charge carriers. Free electron number density is more than hole number density. Where do you find free electrons? In the conduction band. And where do you find holes? In the valence band, correct? Here also conduction of electricity would take place, correct? But it will be in the form of bound electrons, not in the form of free electrons. Free electrons are here, correct? But that conduction of electricity through bound electrons or through holes will be very low conduction, and here majority conduction is carried out by flow of free electrons, correct? That is in the conduction band, got it? Fine. Now we go for second type of semiconductor called P-type semiconductor. Out of tetravalent semiconductor, say tetravalent pure semiconductor, out of tetravalent pure semiconductor, if you want to have P-type semiconductor, then you are supposed to add impurities in that which are trivalent, having 3 valence electrons. They are, for example, just remember aluminum, gallium, indium, aluminum, gallium, indium, out of which at present we take aluminum, correct? Aluminum has atomic number Z equal to 13 and it is found to be trivalent, fine. Now tell me, same proportion we have for aluminum impurity also. For every 10 raised to 6 silicon atoms approximately, we have inclusion of aluminum atom just by 1. Then in 1 mole silicon crystal, how many silicon atoms are there? Approximately 10 raised to 23 silicon atoms, for which the number of aluminum atoms will be how much? Let us find out. This into this upon this, so it is 10 raised to 17 aluminum atoms, 10 raised to 17 aluminum atoms. Now tell me, when you are doping the crystal with aluminum impurity, naturally at certain positions instead of silicon you will find aluminum. Come on. Suppose here we have, instead of silicon we have suppose aluminum. Say this is aluminum atom. Okay. Here I am writing aluminum. Fine. Now tell me, because this is trivalent, it will share only 3 valence electrons in formation of 3 covalent bonds. Suppose it gives 1 electron here, 1 here, 1 here, and suppose in this 4th bond it cannot give any electron because it does not have now, correct? So now you will not have any electron here. So because of deficit of electron, because of absence of electron, you will have one empty space in this covalent bond. It is called hole, but mind well, it is not a free hole. What is the difference between free hole and hole? Free hole has a tendency to attract electron. This does not have a tendency to attract electron. Definitely it has tendency to accept electron. Because such holes can accept electron, we call these trivalent impurities as acceptor impurity. Pentavalent impurity is donating the free electrons, that's why we call them donor impurities. And these trivalent impurities are accepting the electron, that's why we call them acceptor impurities. Okay. For inclusion of 1 aluminum atom, if you have one hole, then for inclusion of this many large number of aluminum atoms, we will have that much large number of holes also. That's why I am showing you very large number of holes. Fine. But don't forget, at room temperature, some of the covalent bonds are getting broken, releasing pair of free electron and hole. But because at room temperature, very few such covalent bonds are getting broken, then we will have very few electrons liberated this way. So number of electrons is very small, number of holes is very large. That number which is very small, it is called minority charge carrier, and that number which is very large is called majority charge carrier. So here number of holes is very large, so right now holes are becoming majority charge carriers. If holes are becoming majority charge carriers, then you know hole behaves as if it is a positive charge. As if it is a positive charge. So what is positive? The first letter of the word positive is P. That's why we have given the name, come on, P-type semiconductor. P-type semiconductor. Got it? Fine. Now tell me, here also don't be misguided that this is electrically positive. No, it is electrically neutral. Because in P-type semiconductor, we have either silicon atoms or aluminum atoms. But whichever it may be, might be silicon, might be aluminum, all the constituent atoms are electrically neutral. So as a whole, the whole crystal, whole semiconductor will be also electrically neutral. Fine. How to explain the conduction of electricity in this P-type semiconductor? Using band diagram. Using band diagram. I am showing you. The lowest band is, come on, valence band. The uppermost band is conduction band. Value of energy of electron in the valence band I am showing by symbol EV. Energy of electron in the conduction band I am showing by symbol EC. And so far the energy corresponding to such hole is concerned, it is same as this energy of this electron, and that energy we have calculated, we find it very close to this valence band. Here energy of donated free electron was found to be very close to conduction band. Here energy of hole, I mean energy of its companion electron is here. Its energy is found to be very close to this valence band. That's why I am showing the energy levels in the form of very small horizontal line segments, and that too at the same height, because all of them have same energy. That's why. Now tell me, here we have holes, fine. But tell me, this gap of energy is found to be nearly 0.05 electron volt, and already this crystal has absorbed thermal energy from surrounding, which is definitely greater than this, and if it is greater than this, then the electrons from valence band will get migrated to these holes. So they will make transitions from their energy level to these holes, and then these all holes will be occupied, will be filled up. But because electrons have left their respective energy levels, then in those energy levels we will have vacant spaces, and such vacant spaces created by the departure of electron in the valence band, in the valence energy levels, is called hole. So here you will have very large number of holes. In the valence band we will have very large number of holes. But mind well, at room temperature, very few electrons get energy to cross this forbidden gap, and they are successful in crossing the forbidden gap. They will come here, but such number is very small. So here also conduction of electricity will be there through these free electrons, but because here free electrons are minority charge carriers, here conduction of electricity through minority charge carriers will be very small conduction, and majority conduction of electricity will take place here in valence band in the form of bound electrons or in the form of holes. Here holes are very large in number, so holes are becoming, come on, majority charge carriers, and because hole behave as if it is a positive charge, the word is positive, first letter of the word positive is P, that's why we call it, come on, P-type semiconductor, correct? And here number of holes is very large, so hole number density is greater than free electron number density. For pure semiconductor, come on, N equals to NH. For N-type semiconductor, N greater than NH, and for P type semiconductor NH greater than Ne. NH greater than Ne. Got it?